after a good lunch with a good talk by Leo Liberti from CNRS and École Polytechnique, and he will speak about random projections in linear programming.
Thank you, Claudia. I'm very, very grateful for this invitation. I really enjoy staying in Rio and in Brazil. The whole time I came, I'm always very grateful to all the people who invite me. So today I'm going to talk about a piece of work of which I'm extremely proud. And so far, it has yielded almost no practical results, but I'm still hopeful. And I'm extremely proud because it sounds a little bit like magic. This is one of the reasons why I like certain branches of mathematics. It's because they really look like they feel like they shouldn't be true, okay? So this is joint work with a brilliant student of mine, Vu Kak Ki. And his first name is Ki. And in French, Ki means who. Okay, so that lends itself to a lot of jokes. For example, there was this secretary of mine who was pissed off with him because he never listens. And she said to him, "Who do you take yourself for?" And in French, that sounds like, "Tu te prends pour qui?" And he said, "Me, yes, me, qui, hello." And this guy, Pierre-Louis Poirion, he's a postdoctoral student. He's also very, very brilliant, but he's French, so there's no such fun. Okay, so this talk is not about a stochastic problem. It's about a stochastic method applied to a deterministic problem, or to a well-defined problem, let's say, where you have all the data. So the next talk will also be about more or less the same topic applied to a different setting, but again, as far as I know, there will be nothing stochastic about it. About the problem. There will be a lot of stochasticity about the method, a lot of randomness. Okay, so this is what I'm trying to do. I'm trying to solve linear programs, okay? I don't think I need to be motivational, or I don't think I need to justify my choice. This is like the single most important technological tool that we dispose of when we solve optimization problems. This thing always works, okay? And it's just about the only thing that always works, LP. I want to take it away from the hands of the simplex method, which is a good method, which guarantees optimality, which, again, always works and very fast. And I want to throw it to the wolves and and throw at it a randomized algorithm. Why is that? Well, first of all, because of the magic of the mathematics behind it. That's my first motivation. It's always having fun, not really being useful. I apologize for that. But the other thing is that, some people consider LP as a done deal, okay? So people like Bob Bixby, the original coder behind Cplex, and now the original, well, the big head behind Gurobi, he says, LP is a done deal. LP, we don't need to work about LP anymore because we know how to solve it. It's solved. And by way of an example, he gives, he says that he has seen Gurobi solve 100 million by 100 million LP, okay? So this is a generic solver that apparently has solved 100 million times 100 million LP, okay? So this is a very, very sparse LP. It probably doesn't solve every instance that you throw at it of this size, but this was like the instance on which they probably trained all of the configuration parameters of Gurobi in order to solve this instance. But this is a success story. And it's quite convincing because in practical problems, are you ever going to need more than that? Probably not if your interest for Gurobi or Cplex is in integer programming, okay? Because integer programming, of course, it's an NP hard problem, so it would be unthinkable to solve 100 million by 100 million IP, okay? So, but if you're in pure LP and if you use LP in order to make sense of raw data, it might happen that you just stumble upon something that is moderately dense. So 100 million is just a dream. And maybe, if you throw Cplex at it, it will just keep looping or it will never converge. Or maybe you need to do it fast, And the other thing is, what if your data, if you have 100 million by 100 million coefficients in a matrix, what are the chances that these are exactly the data you want and they're precise? There's no chance. There must be some error in the data, okay? And so why are you asking for an optimality guarantee if the data is imprecise? So anyway, in order to have fun, I decided to throw some other method at this, okay? And so I'm trading off guarantee of optimality in exchange for an approximate solution, but in a lower CPU time, okay? So, and I'm okay to be wrong with low probability. So this is where the magic comes in. I'm just going to pick a random map T. So you must think of, you can see that this is in standard form, okay? So A would be sort of fat and short, but you must think of this as maybe not too fat and maybe not too short, okay? So M is more or less in the same order of N. Of course, M is small. M is number of rows, N is the number of columns. Of course, the number of rows is going to be smaller than the number of columns, but let's think of them more or less in the same order of magnitude, okay? T, this T here, this is going to be very short and very fat, okay? So I'm going to have the number of columns of T matching the number of rows of A because I want to pre-multiply A by T, okay? But the number of rows of T is going to be very, very small, so that TA x equals TB is going to have very few constraints, okay? And then I want this thing to hold with high probability, meaning that if the original system is feasible, and notice I'm not talking about optimality here, just feasibility. If the original system is feasible, I would like the projected system to be feasible with high probability, okay? In order to, and then I want to solve this thing and sort of go back to that one, retrieve the solution of that one. That's the scheme. How do I solve it? Well, I just feed it to Cplex. If Cplex can't handle this because it's too big, maybe it will be able to handle that. Okay, so that's the plan of the talk. I'm going to give you a sort of a little more general setting for this kind of problem. And then I am going to present the main actor of this. And this has been around for a while. This has been proven in the 1980s. Yes?
Previous slide about the equivalence with high probability.
Yes.
So how do you estimate the probability? So maybe my question is too soon.
Your question is too soon.
Okay.
But I'm sure that after my talk you'll have the same question.
So I keep it for after.
Keep it for later. Okay, so the magic behind this thing is the Johnson-Lindenstrauss Lemma. Even just the names, imagine Johnson and Lindenstrauss, they sort of Lindenstrauss. It sounds really well, it fills your mouth. I'm going to briefly talk about the Johnson-Lindenstrauss Lemma, and I'm going to show that it can be applied to both projecting feasibility and projecting optimality. And then I'm going to briefly mention the solution retrieval thing, and this is like, it was a surprise to us. We didn't think it would be a problem, but it was. And then I'm going to show you where I'm at, meaning that what I can solve in practice so far, which is not a lot, unfortunately. Okay, so restricted linear membership. So this is my general setting. You're given a bunch of vectors. Think of them as n vectors, and these are the columns of A plus one vector, which is your right-hand side, okay? And you're given a set X, from which you're allowed to pick your multipliers, okay? So this is a decision problem, and so it's a question, yes or no question. Given all these data and X, is there a vector of multipliers that makes B be a linear combination of the columns of A? Okay, so this is sort of a general setting. Why is it general? Because I'm giving myself a controlled way to pick the X's from. Okay, so this could be, for example, the non-negative orthant, and then you would have linear feasibility, or then it could be the integer lattice, or maybe an orthant from the integer lattice, in which case you would have integer feasibility. It could be something else. And of course, this is not exactly a decision problem. It's more like a schema, because X could be given in a non-compact way, and then you wouldn't be you wouldn't be able to know whether X is part of the input or not. So it's just like a generalization. It's my general setting. Okay. If you could solve these things efficiently, then via bisection, assuming some boundedness, then you could also solve efficiently the associated problem, at least to some approximation. Okay, so that was my original idea. Let's solve the feasibility problems, and then the optimization will come later through bisection. Okay, so how do I do this magical thing by which I just suddenly lose some dimensions without changing anything about the problem? I have this bunch of vectors, a1 to an, okay, and I want to find a k which is much smaller than m, and these points, the sort of corresponding points, a1 prime to an prime, in Rk. Okay, so these are in Rm, these are given, and I want to find these in Rk, such that these two matrices, these two sets of points, they have almost the same shape. Okay, and almost the same shape doesn't mean a thing. So what is the shape? Well, I thought, okay, what preserves the shape? If I do rotations and translations, that preserves the shape. Okay, so maybe congruence could be a good meaning to attach to the informal word shape. And if I want to do approximate shape, what happens? Well, let's look at this, okay? So if congruence is basically the preservation of all the Euclidean distances between all the pairs of vectors, okay? And so we have for each pair of vectors, if I'm not exactly preserving the two norms, these are all two norms, okay? If I'm not exactly preserving, but just, you know, approximately preserving in a multiplicative controlled way, all of these pairs of vector lengths, maybe this could be a good definition of an approximate shape. Okay? And in order to preserve the approximate, for these A and A prime to have almost the same shape, I would need to verify that A and A prime satisfy this thing. Okay? And this is very close to the statement of the Johnson-Lindenstrauss Lemma, which is going to be up next. So the strategy now appears clear. If I cannot solve this problem because it's too high dimensional, but I can find these low dimensional vectors that have this property if and only if with high probability, then I can just solve the low dimensional problem, maybe many times if the probability is high enough or low enough, but I can sort of come away a happy person because I'll have solved that one. Okay? All right. So where does the magic come in? In low dimensions, it doesn't. If you try and do this, if you try and project something in some ways in a general form, and your algorithm has to be general, and you're just too few dimensions in which to live, it's just not possible. It's not gonna happen. Okay. However, there are results. This result, the Johnson-Lindenstrauss lemma, talks about a probability of this happening that sort of approaches 1 asymptotically, okay? So there is a dimensionality that grows, and the probability of this approximate shape being held that grows with it, okay? And it grows fast. So the theorem is not stated in a probabilistic way. It's stated in an existential way, okay? So given a matrix or a set of points in Rm, okay? And this set of points has n points, and given an epsilon, then there is a lower dimensional space, so k is the dimensionality of the projected space, and this k is more or less of the order of 1 over epsilon squared times logarithm of n, okay? And the k times m matrix T such that this happens, okay? So you see you're projecting x and y for every x and y in A, you're projecting tx and ty, and their distance is sandwiched between the 1 minus epsilon times and 1 plus epsilon times the original distance. So that means that this thing has low distortion. Okay, so how do we prove the existence of this K? Well, we can simply, the way Johnson-Lindenstrauss proved it was by basically pulling out of their hat a random subspace of the Rm. Okay, this random subspace was carefully constructed, and it's essentially equivalent to sampling T component-wise from a normal distribution which has mean 0 and standard deviation 1 over square root of k. Okay, so then A and Ta have almost the same shape. Notice that this thing makes T very dense, actually completely dense. Okay. But there's also some sort of sparser approximation of this that also work. Like, for example, Acleoptas proved that you can take this distribution where you have Tij equals to -1 with probability 1/6, and Tij equals to 0 with probability 2/3, and Tij equals to +1 with probability 1/6. So this is kind of the coarsest discrete approximation of a Gaussian distribution that you could imagine, and it still works, okay? Okay. So you can prove that the distortion has low probability, and you can actually prove something quantitative about it, meaning the probability of getting out of your comfort zone around the mean is bounded by 1 over n squared, okay? So if you do the union bound over all of the possible pairs of, in the set A, you come up with something that the probability of A and Ta having almost the same shape is greater than or equal to 1 over n. So at worst, you have to sample T n times, okay? Which might be a lot, but you know what? The important thing for practical computation is not really the worst case. Even if you are not preserving 1 or 2 distances out of many millions, I don't think that that's going to make a practical impact, okay? That's my bet. In fact, I have some sort of computational evidence that gives me reason on this. The real thing here is that the average is conserved, okay? So T is sampled by a normal distribution. So you have as many -1 multipliers than +1 multipliers. And so this is what really makes this work, okay? And yes, you need the distortion to stay close. But even if you exceed here and there, it's not going to be such a big problem. Okay, so I looked for a proof of the Johnson-Lindenstrauss lemma that was clear enough in order for me to present to audiences. I didn't find it. There are some very short proofs, but the short proofs have some non-intuitive lemmata that are purely algebraic. So you just have to sort of understand them and say, oh, okay, that's it. And they concern the behavior of certain exponential functions or logarithmic function. Instead, in order to give you just the gist of it, and in a way that I personally find geometrically clearer, let me argue in this way. And it's not a proof, okay? It's just to suggest what's going on. I'm going to argue that there is one setting where it's relatively easy to prove concentration of measure, and that's the surface of a sphere. And then I'm going to use a stereographic projection to show you that the Johnson-Lindenstrauss lemma is more or less that, okay, the projection. So here you see 3 spheres, and I want you to pretend that this is in 2 dimensions, and this is in 11 dimensions, and this is in 101 dimensions, okay? And the blue band is a band around the equator, actually any equator, okay? And this band contains 90% of the surface of the sphere, okay? And in 2 dimensions, your 90% of the surface of the sphere leaves you poles that are very tiny. But in 11 dimensions already, you get half here. So 90% of the surface of the sphere is contained in basically just a height of half between the center of the sphere and the North Pole, okay, or the South Pole. Yes? So this is like an intuitive, this is a circle representing a sphere, okay? You see 3 circles with blue bands. In fact, I want you to think in 11 dimensions here and in 101 dimensions here. So use your powers, your special powers, and figure yourself these 101 dimensions, okay? So the important thing is that you can see here that this is concentrating its measure. The measure of the surface area is concentrating around the equator, which is to be seen as the mean, okay? So how do you prove this? Well, you just do an integral, okay? So if you take this disk and you integrate it, you can compute the area, and you can compute it in terms of the dimensions, the dimensionality of the space, and then you can upper bound. You derive an integral which is more or less undoable, okay? Not in terms of the elementary functions, but if you allow yourself the error function, then it is doable. And this is the depiction of an error function. As you can see, it falls hopelessly towards 0 very, very fast, okay? And this is what's important. This is why this thing is getting very, very close to the equator very, very fast. Okay. So now let's look at the Johnson-Lindenstrauss lemma. Here I have, this is a different form of the Johnson-Lindenstrauss lemma where you only care about the norm of a single vector. You don't have the distance between 2 vectors. You have the norm of a single vector, okay? So the same thing holds, meaning that the norm is going to be preserved, okay? So if the given vector has unit norm and you pre-multiply it by your random projector, the expectation of the square of the norm here is going to be unit, okay? And this is really important. This is like your equator, okay? Now you have to argue that the distortion is low, okay? And this is what I figured. Here, I can't see almost anything here, but anyway, so here you got the North Pole, and this is the sphere. You must see the sphere as a very high-dimensional sphere, okay? And you've got this band, okay? Now, the disk here, the pink disk, is basically a projection on a subspace. So this would be the effect of T. If you've got the vector u somewhere, for example here, this dot here is u, okay, and you project it, it goes down onto this horizontal subspace. That's the effect of multiplying u, pre-multiplying u by T, okay? And now I'm saying, look at what happens if your band here is extremely small, which we know to be small because we've proved concentration of measure on the surface of a sphere. When you project it, you either are on the north hemisphere and then you cross it and fall outside, or you are in the southern hemisphere and you cross the inside disk until you touch that, okay? Either way, this thing, although it doesn't grow linearly with the band, when the band is very close, you can approximate it by linear, okay? It's sort of like, you know, tangent being almost close to sine or being almost close to x when it's tiny, okay? By this thing, then you can sort of project this, and this disk gives you the distortion, okay? This stereographic projection essentially proves that the same distortion, the same concentration of distortion that you've seen here, concentration of measure that you've seen here, reflects itself onto this projection, okay? This disk, this pink disk, is, as you can see, it's around norm 1, okay? So here I'm saying that the average is 1, it's on the equator, and the distortion is small, it's on this pink disk. Now, this should be a justification, a geometrical justification or an intuition behind this Johnson-Lindenstrauss lemma. It's not a proof. And I think to make it into a proof, it would be possible, but it would yield a very long proof because you have to sort of do this nonlinear linear stereographic projection, but then you have to have the nonlinear approximation to the height, and so it would make an unwieldy proof, okay? But at least it's by images. Okay, so in practice, there's a couple of crazy guys who have sort of, okay, let me just see, do I have an order of something here? No, I don't yet. Okay, so this, yes, I do, the k here, okay? K is order of something, okay? Order of something, it means that I have to find a constant in front of this order, okay? So k is less than or equal to constant times that function. Nobody knows what the constant is, but these people in 2011 ran a lot of computational experiments in just one application of the Johnson-Lindenstrauss lemma. So for that application, which is the clustering, they found out that this is the constant, okay? I'm sort of ignoring it. I'm taking a hint, but ignoring it mostly. But also they found empirically, and this is I also found that you need to sample T very, very few times, like, you know, once or twice will do. So it's not such an expensive thing. You don't need to sample it n times, okay, in practice. So one thing that is interesting here is that K, the lower dimensional space, the dimension of the lower dimensional space is independent of the original dimension, M, okay? K and M have nothing to do with each other. It's as if I told you that these vectors could live in much fewer dimensions than you thought possible, and actually irrelevantly of what the dimensionality is, okay? This is very, very strange, and it's one of those things that I would call magic, in fact. And it only really depends on the number of points in the set, okay? So if you had n points in the set, n vectors, this is what it depends on. It also depends on 1 over epsilon squared, which is bad, okay? Because if you want like 10% error, you need to multiply by 100. And if you want like 1% error, you need to multiply by 10,000. But then you multiply by logarithm of the number of points in the set. And if you have, for example, images typically, they have millions of dimensions, but you don't have millions of images. You might have thousands of images, okay? And if that's the case, it's like, you know, instead of having millions and millions of dimensions to play with, you have, I don't know, 10,000 or 100 times logarithm of 1,000, which is peanuts, okay? So this is really very, very strong. Okay, so the typical application so far of the Johnson-Lindenstrauss Lemma, well, when I say so far, let's say up until 2008, okay? They've been into clustering, Euclidean clustering, and more particularly k-means and k-nearest neighbors, because these are algorithms where essentially they only deal with the two norm, okay? There's only a Euclidean norm operation on them. And so they, of course, they adapt very well to this Johnson-Lindenstrauss Lemma. So recently I've seen linear regression. Very, very recently I was made aware that Ankur is working on similar things on a different application, which he'll talk about. With optimization, well, you know, linear optimization or feasibility, I have seen nothing so far. So meaning that I believe that nobody has really looked at that. We think it's important to look at it. We think that it's hard because of the non-negative constraints here. This makes it hard. If you only wanted to preserve equality here, it wouldn't be that hard, okay? But this makes it hard because when you pre-multiply by a random projector, you're multiplying everything by plus and minuses. So what you really don't project is the non-negative orthant, okay? If you simply project these things blindly, they will be all over the place, and the solution will certainly not respect that, okay? Okay. So, what did Google do with this? Up until a few months or maybe years ago, I've checked that maybe last year. Every time you did a Google image search, it would present you with, I don't know, maybe 500 images or 1,000 images, but you only see the first page, but if you scroll down, it's immediate. So obviously it's looked for some images, maybe not millions of images, but say 1,000, okay? And to make your life easier, it would present you with an upper row of small thumbnails that of each thumbnail would be a representative of a different cluster, okay? So they would do a clustering in real time, okay? Because your search, they don't know your search, okay? So you search for something, they don't know what it is, but they present you with not only the findings, but also clustering, okay? How do they do it so blindingly fast? They do it exactly with a result like that one, okay? I don't know if they precisely use that, but it's certainly the case that k-means is the success story in the practical application of Johnson-Lindenstrauss Lemma. Here I've done a very simple test. I looked for spaghetti code. And of course, there's some code, but there's also some spaghetti. And you can see that this is the original images. And the clustering with k-means recognizes one. And then more or less everything is the same cluster apart from the two spaghetti images. Okay? And if I project it, I get exactly the same clustering, but in much less time. Okay, so how do we project feasibility? Here's the easy cases. First case and second case are about a certificate, meaning that you know what x is, okay? So you're given the vector x, you know it. So you know that b is equal to this linear combination where x is given of the column of a's, okay? Then, of course, by linearity, TB is equal to the linear combinations with the same certificate of the columns of A. Nothing to prove. Secondly, a little bit to prove is that if B is not this particular linear combination of the columns of A with the x given, then the probability that TB is not this particular combination approaches 1 as k increases, okay? So this is what we want. Also, if B is not a linear combination of columns of A for every x, for every y into the set big X, where the cardinality of big X is finite, so this is not yet applicable to linear programming, then the probability of having B not a linear combination of the columns of A for all these certificates in big X, that also approaches 1 as k grows, okay? And as you can see, we have the cardinality of x here, which is a short sign that I'm using the union bound on case 2, which is exactly the case, okay? So the only thing that probably requires a comment is this case 2 here at this stage. And essentially, I am reducing this to this simple statement. if z is the non-zero vector, then there is a constant c such that the probability of projecting the zero vector into something non-zero, to projecting a non-zero vector into zero is very low, okay? So if you have a non-zero vector and you use a random projector, chances are you will not project it to zero. It sounds intuitively okay. Huh? And
C is a universal constant.
well, is it universal? I'm not sure that it's universal in the same sense that Newton intended is universal constant. Maybe there is a universal, actually there is a universal constant. But if you want to do practical computation, that universal constant, not only it's elusive, but it's probably completely useless because it'll be like 10 billion or something. So I'm not really sure that I want to bank on this universality. I try and do a little computation, see what sort of I come up with, and then form my own idea about the universality of these constants.
It only depends on the normal distribution. That's the only properties.
Yes. Mathematically speaking, yes. Practically speaking, very much no. Meaning that sometimes you can, get away with a low constant, and I don't think that low constant would be okay for every instance. Okay. All right. So if you have this, then you apply it to ax minus b, and you retrieve exactly this. Okay. Now, these are okay for checking certificates 1 and 2, but they're not really usable for anything else. Whereas number 3 could be used for integer programming, and in those cases, sorry, number 3 is this one. They could be used in integer programming in those cases where x is polynomially bounded. So if you've got some like for example, a knapsack set in this case, you can prove that if d is fixed, then this set has a polynomially bound number of solutions inside. And then you can argue that the probability of this set being projected into something infeasible, if the original set was infeasible, is high enough. Okay? The other thing to notice is that we have absolutely no problem with feasibility. Okay? So the game here is not projecting feasibility. That's obvious that you project something feasible into something feasible because t is linear. Okay? The real issue is that if your original system is infeasible, you don't want your projected system to be feasible. Okay? That's the real difficulty. Okay. So when x, that also gives, the number 3 also hints as to why the case of linear programming is not as easy. Because in linear programming, this thing is uncountable, okay? So the number of possible certificates are just the non-negative orthant. Okay, so we sort of worked out a Farkas lemma in a projected way, okay? So if you're given all these vectors, all the data of your problem, the objective function C, and the right-hand side, and the columns of A, then you have this situation which describes exactly the Farkas lemma, this kind of separation if it's infeasible. Then this is projected, meaning that TB is not in the cone of TAs with high probability, and you do this by, this is not a difficult proof, it's simply a trick-ridden proof. You have a lot of tricks for expanding two norms and getting rid of double products and so on. Okay, so you come up with TC and TB in dot product being exactly bounded in the same way as Farkas lemma. So essentially, I'm projecting Farkas lemma. Once I've got this, I can argue that I can do linear feasibility. Okay, I can project linear feasibility instances into their projected counterpart, lower dimensional counterparts, and come away with it. Okay, so how is this useful? Well, all these previous results look like this. If the original LFP is infeasible, then the probability of the projected LFP being infeasible has high probability when k increases. Okay, and P and R are two polynomials, one of n and the other of epsilon. Okay, so basically you want this thing to be, if you want a clear statement of what you're doing, meaning that you want to choose your delta such that this probability exceeds 1 minus delta, then you replace all this with a delta and work out what it means in terms of n and epsilon. Okay, and that gives you sort of the analysis into what you need epsilon and n to be. Okay. Okay. So that's applicable to LFP. this sort of separation, this projecting separation, but it depends on this epsilon in a way that we don't like. Specifically, finding the best epsilon is itself an LP, and because we're trying to solve an LP by a different, it's an LP that is as big as the original one. So essentially, we don't know what epsilon is, and there's no way to find out, and even postulating the epsilon is not something that, that we like. There's also another observation, which is actually more important. We know that this result gets harder and harder to enforce as soon as the cone gets opened, okay? And the cone getting opened is something important, because if you're doing bisection, your cone sort of varies the aperture. Okay, so instead of projecting Farkas lemma, we proved a different theorem that projects the minimum distance to a cone, okay? So this turns out to be more powerful because it doesn't have the dependency on the angle of the cone, but it's much more complicated to prove. So I'm not going to go into the details here. It's not a difficult proof, but it's long. It's got a lot of details inside. Okay, so this result also works, by the way, with non-pointed cones, which was not the case in the previous instance, okay, in the previous theorem. So we appear to be all set for LFP. So feasibility projection theorem essentially says that given a delta, there exists sufficiently large M and N such that for any LFP input A and B, we can sample a random matrix T such that K is much smaller than M and this property, okay? So if the probability of LFP being feasible implies and is implied by the projected LFP being feasible exceeds 1 minus delta, with the feasibility being probability 1, actually certainty, and the infeasibility being the one that bounds the probability. Okay, so that ends feasibility. Now, optimality. At the beginning, I wanted to do this via bisection. And then I did it, I implemented it, and it was crap. It was very, very crap. Unreliable, slow, couldn't solve anything, nothing. Okay, so we worked some more, and we were able to prove that in fact, that any method would be okay. It's not just bisection. So the fact that bisection works is a consequence of projecting feasibility, okay? But once you think about what it means, it's like if bisection works, it means that the optimum is preserved, okay? Because otherwise a bisection wouldn't work. But if the optimum is preserved by projection, then any method can be used. This is more or less what's behind this. So let's call P the original problem, TP the projected problem, and this is the value of P, the value of the optimal objective function value of P, and V of TP is the optimal objective function value of TP, of the projected problem. Okay? So we assume that P is bounded, so its feasible region is bounded. We assume that it's non-empty. And we assume also that the boundedness takes this form. So essentially, if you don't want these xj's, the variables, at the optimum being too wild, okay? So the sum of all your variables at the optima must be bounded by a given theta, okay? All right, so then we have this theorem that says that given any delta, the optimal objective function value of the original problem minus delta and the optimal objective function value of the original problem sandwich the objective function value of the projected problem, okay? So the easy part is VTP less than or equal VP. Why is it easy? Because TP, the projected problem, is in fact a relaxation of the original problem. You're taking all of the constraints and you're basically making linear combinations of the constraints, okay? So it's like an aggregation, and that yields a relaxation in a very natural way. I'm giving you the hard part without the hard part, okay? So this equation, where is it? This system is equivalent to P for delta is equal to 0. Why? What does it say? It's saying that the objective function value plus a slack variable is equal to the optimal objective function value, okay? Delta is equal to 0 here. AX is equal to B are the original constraints, and this is the non-negative orthant, okay? So that's a system. If you knew VP, this system would be exactly equivalent to solving P, okay? However, for delta, because this is the optimal objective function value and we're minimizing, you cannot find any value of x's that will yield any lesser value, okay? So that means that if for delta greater than 0, this is infeasible, okay? Now, I would like to say, since this is an infeasible linear system, I'm going to project it by using our results that I just proved in the first part of the talk, okay? And this is where I'm hitting all the hard part, because in fact, that result is in function of the distance to a cone, but here we don't know how to make use of it. So instead, we have to sort of reprove that theorem, the infeasibility projection theorem, from a different point of view, and it uses different tricks, different details, so this is the hard part, let's say. But I'm just going to say by feasibility projection theorem, then the projected system is also going to be infeasible with high probability, okay? And hence, since this is infeasible, if I take away the slack, I have the Cx less than Vp minus delta is infeasible, which means that Cx greater than or equal to Vp minus delta holds with high probability, okay? And so this is the other part of my sandwiching. Okay. Solution retrieval. When I started off this, I didn't worry about this. I just thought, okay, I'm going to solve the projected problem in a flash because it's small, and then I'm going to take the solution, and it's going to be the solution of my problem. Wrong. In fact, we got so many empirical failures that we were able to prove, after a while we tried to prove it, and it came out, meaning that we were able to prove that, in fact, if you take the solution of the projected problem with probability 1, it will not be feasible in the original problem, okay? So there's some more work to do, okay? Luckily, there is the dual, okay? So if you look at the dual here, and you think of the projected dual will have something like this, TA transpose times y prime, okay? Y prime is the solution of the dual. Notice that if you solve an LP, you have both the primal solution and the dual solution, okay? So we know once we solve TP, we know y prime, okay? So this thing, if you write it like this, you can just use associativity to see that this is now T transpose y prime is a solution of the dual, not only of the projected dual, but of the dual itself. The objective functions are exactly the same, okay?
So
because
means feasible or means optimal?
So this is feasible in the dual, but the objective function values, they are the same. It's another line of proof, okay? So this thing will say that it's optimal in the dual. So this is T transpose y prime is a solution of the dual, not the projected one, the dual itself, okay? So we can compute an optimal basis, and from this basis retrieve the prime, okay, through complementarity conditions. Okay, so I tried to put all this to good use on my computer, and first of all, I'm going to show you some results on linear feasibility problems. There is no objective function here, and all these things, they are infeasible, of course. We only generate infeasible systems because we know that the feasible systems are going to be projected, okay? So these are infeasible systems generated uniformly, either with the coefficients either in -1, 1 or in 0, 1, okay? And the 0, 1 coefficients, they yield immensely easier, much easier instances, okay? So these things have accuracy 0 here. What it really means is that I'm not scaling up to sufficient sizes, okay? I'm projecting to problems that are too small, okay? But if you look at coefficients that are in a positive orthant, then everything is fine, okay? So that means that my constants are not being held to gravitational standard, okay? So they're not being universal constants. My constants are guessed, and they're guessed poorly. And they're guessed well enough for this case, but not for that case. Why are the two cases different? Because if you have coefficients in -1, 1, you might as well have very open cones. But if you have coefficients in 0, 1, you cannot really have open cones, okay? And this is why. It makes it easier.
So what does it mean? Can you uniform -1, 1?
So I pick, yes, every independently, yes.
You take all independently
Yes.
as uniform.
Yes.
0, 1 of certain size.
Yes, the sizes are, there's a few sizes here.
Reasonable size.
Reasonably big sizes for a dense LP. Okay. Now I'm going to focus on a single LP instance. Okay, now it's an LP, so it's got an objective function, and it's just one instance. Why just one? Because I did it yesterday. Okay, and I had no time to do 2 of them. But I can certainly do 2 of them in the next few days. Okay, so this is a single random dense LP instance. It's generated in this way. It's 5,000 times 5,500 binary matrix with density 0.8. Okay, and X is a basic solution with non-zero sampled uniformly in this set, so it's all integer. Okay, so it's kind of like it looks like a combinatorial problem. Why is that? Because I'm interested into branch and bound that every node has usually it's used for combinatorial problems. The matrices are often 0, 1, and at each node you have to solve an LP relaxation. Okay. All right. So B is computed by simply multiplying A and X. So I know it's feasible. Everything is fine. And C is picked to make X optimal, i.e. Cj is equal to 0 if and only if Xj is a basic variable. Okay. Now this thing has a lot of favorable properties. Okay. First of all, the fact that I'm picking coefficients from 0 and from 1 makes the cone relatively small, so it's okay. It's I'm having it easy. Okay, I'm making my life easy. The other thing that makes my life easy is that C is lower bounded by 0. Okay, so the objective function value cannot be any lower than 0 because the coefficients are all non-negative and the variables are all non-negative. Okay, so I'm using Cplex and I'm using the barrier subsolver for the projected problem because it helps dense problem. I don't know why it shouldn't. I mean, Cplex people say that the barrier problem should be used on sparse. The barrier algorithm should be used on sparse problems. I'm finding that these problems are better solved by the barrier algorithm, and I'm letting Cplex choose for the original problem. And I'm testing a few configurations, okay? So the epsilon here is 0.05, okay? So I'm allowing 5% error. And the universal constant is 1.2 here, okay? So K, the projected subspace, is almost as high dimensional as the original subspace, 4,134. The original subspace is 5,000, okay? So, of course, this is 0 value, and the original problem is solving 700 seconds by Cplex, and the projected problem takes longer than that, okay? This is a measure of the infeasibility, okay? There is some error. I'm not catching exactly a feasible solution. And this is quite a low error. This is the definition of the error. I'm summing up all of the mistakes, all of the errors of each constraint, and then I'm dividing them by essentially the sum of all the right-hand sides. It's the scaling. I could choose another. I guess that this made sense to me because in this particular instance, you can see that A is a big matrix, so B are likely to be big. Okay, there's a lot of 1s here, and so these B's are going to be large. Okay. Okay. So, but as soon as I go to 10% error, my CPU time falls dramatically. Okay. So actually, and here I'm using a sampling which is not the best possible, the fastest possible. I'm using a matrix multiplication, which is definitely not the fastest possible. I'm using basically old substandard technology, and I'm comparing, and then I'm using Cplex, okay? But I'm using the barrier algorithm, which is not the best algorithm that Cplex has to offer. And I'm comparing against the best, which is Cplex on a simplex algorithm, and yet it's taking less to solve. So this is the positive spin that I can give to this talk. This serves a purpose. And the purpose it serves is to be able to solve one randomly generated instance. Then I picked a few of the big instances in the netlib, which is a publicly available library. And these unearth the bad things in this. Well, let's say they unearth my lack of progress in this field. And they unearth the fact that I still need to do some work in order to get this to work. Okay? And so these are the instances that they're moderately small for my needs, okay? And moreover, they're completely sparse, okay? These are real problems from the netlib, and they, they can be decomposed. They come from complete sparsity. They have a lot of zeros, so they're not a good benchmark. Okay, so this is the number of variables, and this is the projection. Okay, you can see that the projection really is like almost the same as the original problem. So I don't expect any saving, and in fact, I don't have any savings. This is the CPU time that Simplex has, and this is the CPU time that I get. So you can see it's like 2 orders of magnitude. It's horrible. So I definitely do need to do some work here. However, I can already see that many of the relaxations are pretty tight, and that the infeasibilities are really minor, okay? So one possible suggestion would be to, I don't know, to do some kind of very fast stochastic gradient descent in order to take this to full feasibility. Another idea would be to take the famous 100 million by 100 million matrix, and let's see what we can do with that. So I think that this is just the beginning. So we're not ready to beat Simplex yet on sparse LPs, but we can beat Simplex on at least one instance which is dense. So that I take that as heading into the right direction. What we want to do next is we want to try the dual LP. Essentially, there is a completely orthogonal theory for the dual that instead of reducing the number of constraints, it reduces the number of variables, okay? And you have to take the LP in canonical form instead of standard form. But then everything else works the same way. The only thing is that it might be easier to retrieve the solution because we don't need to go to the dual. We're already in the dual. What we really dream of, but I don't know how to go about this, is to project both row and columns and still maintain optimality. Thank you very much.
Thank you, Leo, for the nice talk.